it's a deep dive into negative pressure regulated gas valves. So this is the type of valve that we use on effectively all modulating condensing equipment. For some of you, it's probably a review. For some of you, hopefully there's some new stuff you're going to learn. And I'd like to do more of this kind of presentation now that I'm in training. I'm excited that I'm going to be able to sort of dive into some of the training topics that have always interested me a bit more. Hopefully they interest you guys just as much. And so I would appreciate any feedback you can give me tonight. Love it, hate it, let me know and we'll go through. I would encourage lots of interaction, so keep Ted and Steve busy asking questions. I think as we go through, hopefully you get something out of it. And, there we go. Sorry, using the trackpad on the computer here, it doesn't work quite the same. So we're going to go over the basic parts of a gas valve, the operation of the valve, how the valve and the venturi interact together, what the heck the Bernoulli effect is, and also how a venturi works. So that's the highlight. All the presentation is just on that. So we're going to start off with a very basic rendition of a gas valve. You'll have to excuse the animation. This is the best I can do. So I've represented here a basic gas valve. So on the left-hand side coming in, we've got our gas entering the valve. We've got our plunger assembly up top. This blue box is the solenoid. And sort of this represents the most basic thing you could imagine a gas valve would do. So we're gonna turn this on and just see what happens. So we've got a plunger there. This is what controls or stops the gas flow. Our gas comes in. Obviously, our gas is going to fill the bottom of the valve, but cannot pass through until such time as the solenoid opens. The gas valve body is there just to contain the gas, give you something to connect onto. And when we open the valve, what's going to happen is gas obviously is going to pass around this plunger out through the gas line into whatever's connected on the other side. So a couple of questions when you first look at this. One thing you'll notice is when the gas comes in, it forces this gas valve closed. So effectively, the higher the gas pressure, the harder it is for the valve to open. And one of the questions I'd like everyone just to think about for a sec is, why is it that way? If you look at any gas valve, so I don't know how many you've disassembled, but if you pull apart just about any valve, you'll find that the plunger is set up exactly like this. It has to overcome the gas pressure in order to open. And so I guess the question for you guys to think about is why is that? So we'll run through this again. Now, another question for you related to this exact valve setup is, can anybody see where this valve may not be the best option for our boilers? So the question I'm asking here is, how does the gas valve or how does the gas pressure affect our gas flow in a scenario like this? So give that a thought for a sec, and then we're going to move on to the next step. So we're going to do a real quick poll here. I don't remember putting this close, but apparently I did. So the poll question is, guys, yep, we're going to get Steve to launch the poll and give me an answer. So basic question, why do we have the plunger set up so that the gas pressure effectively holds it closed? Why are we making the solenoid fight against the gas pressure is the first question. So first answer, obviously the designer had a bad day. This happens, and that is potentially an option. It's to help prevent gas flow, it's to help the gas pass through the valve more easily. It's to prevent gas flow if the pressure is too high. It's to allow the solenoid to regulate the gas flow. So everyone type in your answers and let me know what you think the answers are.
You have 60 seconds to answer this question, at which point I will allow Ted, if he wants to read the answers of how they're coming in. Totally up to you, Ted, or I can do it.
No, that's fine. We've got basically 63% choosing number 3 to prevent gas flow if the pressure is too high, followed by a fairly healthy 27% to allow the solenoid to regulate the gas flow. 5% think it's to help the gas pass through the valve, and nobody seems to think it's because the designer had a bad day.
You'd be surprised. Sometimes that is the answer, but not in this
So,
case.
Not in
so we're
this
giving
particular case, apparently.
10 more seconds. See if you guys can increase your portions there. 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, I'm going to
All
close.
right, two-thirds, a full two-thirds choose number 3 to prevent gas flow if the gas pressure is too high.
Yep,
So
and that is effectively the truth. So the 2/3 of you are correct. The idea is that the valve has a fail safe, so that if for some reason you put, for example, I think Enbridge Gas in St. John supplies gas to our building at something like 65 psi. It then gets regulated down to 6 or 7 inches at the boiler. If you apply 65 pounds to the valve, it effectively just locks it closed so that it cannot open and you can't have excess gas flow. So it's a safety design. So it was done that way very deliberately. The
Do you have an idea
solenoid,
what that threshold is, Dave?
the threshold at which the valve will no longer open.
Yeah.
I know it's higher than 48 inches because I've actually seen pressure in our building when one of our regulators broke where we had 48 inches on the valve and it opened just fine.
Well,
So it's a fairly high threshold.
apparently, yeah.
very high.
Yeah, very high. Yes. So so the valves will open under a tremendous amount of pressure, but obviously if you put a huge strain on it, it doesn't do anything. The other good news about that is, provided the valve doesn't actually open, the diaphragm or not the diaphragm, sorry, the plunger is quite a robust component. Even if you were to accidentally put 60 pounds to it, my guess is it would do no damage unless the valve somehow managed to open. Now, once it opens, the internal parts of the valve are a little more sensitive. You probably can and will do some damage to those. And most gas valves have some sort of warning that says if you apply more than 28 inches of water column, you run the risk of damaging the valve. And so that's obviously something you want to keep in mind.
Mylek would like to
Now,
know. Mylek would like to know, when you had 40 inches of water column, did you do a combustion test on that unit?
well, the good news is the regulator was seeping. So as soon as it opened, the pressure regulated off to 7 inches and maintained. So I actually did do a test and it was okay, but within about 2 seconds of the valve opening, the pressure leveled off again. So
Wow.
for those that mentioned the solenoid, with the solenoids used in all of the gas valves that NTI uses at least, none of these are what I would call a regulated solenoid. They're on or off. So they are open, closed. There is no variable electrical current going through the coil. So once these things open, they're fully open. Once they close, they're fully closed. There are other types of solenoids that can be regulated, but I haven't come across one, at least in the type of stuff that NTI is using. So we've got another gas valve here. For anybody in the previous section, I'd asked you, how does gas pressure affect the flow through this gas valve? And one of the problems with a gas valve that's set up directly like this, where the gas coming in pushes past a restriction and then out to the gas line, is the higher the incoming gas pressure, the higher the outgoing gas pressure. So incoming pressure is directly correlated. Obviously, you can imagine a scenario where we are at 48 inches, that's going to really overfire your boiler quite a bit. One strategy people have tried in the past is to put an orifice in. So an orifice kind of does what you might expect. So we've got gas coming in, it's going to apply upwards pressure on our plunger, preventing the valve from opening. The solenoid is designed to overcome this under normal conditions. Our gas is going to flow, and then the restriction from the orifice is going to limit the amount of gas that gets out of the valve to some lower value. Unfortunately, in this scenario, we still run into the same issue, which is that even with an orifice there, the outgoing gas pressure is 100% directly tied to the incoming gas pressure, which, if all of your propane regulators out there are working perfectly, that's not a problem. But we all know that those conditions don't really exist. So another option, of course, is to put an adjustable gate valve. And this is my simulation for the type of gate that's actually in the valves that we use. And it is very literally a gate valve at the outlet of the valve. When you tighten that screw, you're pushing a gate across the outlet, which is kind of like an adjustable orifice. Oftentimes we'll use the gate valve in conjunction with an orifice to help the valve better control the flow of gas overall. But this still leaves us in the same problem we had before, which is the incoming gas pressure and the outgoing gas pressure are still directly correlated. And if for some reason you have a change in incoming pressure, even though you may have set an outlet pressure, the second your inlet pressure changes, this is also going to change. So what we're missing is a regulator assembly. And the regulator assembly on the gas valve is very similar to the gas regulator that you would use in the field to feed the building. It works on the same process. So we've got a plunger. So in this case, we've got a single plunger that's the solenoid to open the valve. And this assembly consists of a diaphragm. So what the diaphragm does is it's to contain the gas flow. But the diaphragm serves two purposes. Not only does it prevent gas from leaking, its job is to, I'll say, amplify or provide a large surface area for the gas pressure to act on, so that that pressure can directly act on this second plunger, the one over here. So this plunger and this diaphragm are directly tied together in a solid unit. So when one moves, the other one moves. There's typically a spring somewhere in there, and the spring is in the regulator assembly, just like it is with the big regulators. What this is designed to do is to help regulate the diaphragm. Now what happens is when the solenoid opens, we allow gas into the valve, but in this particular scenario, the valve still isn't open. Gas is not passing through. There's nothing coming out of the outlet of the valve. So the question becomes, what opens the valve? Another part that is missing from this picture is this little vent adapter or vent regulator. And what this does is provides a port to the outside world or to the atmosphere. At least that's one thing that it can be used for. And so now what you'll notice happens in this scenario, as our gas comes through, it again pushes down on the plunger as a fail-safe, preventing the valve from opening. And then what will happen is suction pressure coming from our combustion blower fan is going to drop the pressure in the area where the cursor is. That's going to force the diaphragm to want to lift up. Provided we're open to the atmosphere, atmospheric air is going to flow in if the pressure inside the valve is less than it is outside. And what should happen is question number 2. How does the atmosphere affect our gas pressure?
So I guess I have to launch this one. Here we go.
Yep.
So how does the atmospheric pressure affect a gas valve? The atmospheric pressure reduces the gas flow. Answer number 1. Answer number 2 is the atmospheric pressure increases the gas flow. Answer number 3, the atmospheric pressure affects the gas to air ratio. Or answer number 4, all of the above. Please check
for those that are looking at the question, if you can still see the regulator assembly on screen.
No, they can't. Nope.
No.
Okay.
It's all they can see. All they can see is the question and answers right now. So if you would answer the question, you got 60 seconds to do it, and then Dave will answer the correct answer and show you his demonstration on that.
So 73, almost 3/4 believe it's all of the above. Just under 1/4 are saying atmospheric pressure increases the gas flow, and 14% are at the atmospheric pressure affects the gas air ratio, and nobody thinks that atmospheric pressure reduces gas flow.
So keep answering. You got another, I'll give you another 15 seconds. That's 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Okay.
Nothing's changed.
Just under 2/3 think it's all of the above. And then followed by atmospheric pressure increases gas flow, and trailing both of those is atmospheric pressure affects the gas air ratio.
Yeah, and the answer is all of the above. So depending on what the atmospheric pressure does, depends on what happens to the outgoing gas pressure. So in this scenario, if the gas pressure inside the valve here is pushing down on the diaphragm, that means the atmospheric pressure out here in the world is pushing up on the diaphragm. These two pressures are competing against each other. So if we raise the atmospheric pressure, what's going to happen is more pressure is going to push up on the diaphragm. Because the diaphragm is directly tied to the plunger, it's going to lift the diaphragm higher, allowing more gas through the boiler. If we have a change in atmospheric pressure and we get a very low pressure system, not only do you get a bunch of bad weather, but you're also going to get reduced gas flow because there's less pressure pushing up back against the gas, which means that we're going to get less gas through the system. And that's done for a very specific reason. It means that as we get changes in atmospheric pressure, which does change quite a bit, it could go from what's the range typically? I'm trying to think. I'm thinking in kilopascals, which isn't going to mean much to the audience tonight, but it goes from like 99 to 102. And I know that from listening to my local weather network. I'm in Canada, sorry. I don't know, 14.6 to 14.8 pounds per square inch, something like that, roughly.
Hopefully.
So as that pressure goes up and down, what that's going to mean is if we have a high pressure system moving through, that means the air is more dense. It means we've got more air available to burn for every cubic foot of gas. So that means we need more gas. So as the air pressure in the building, in the building or on the valve increases, it forces the valve open just a tiny bit more to allow a tiny bit more gas. If for some reason the incoming gas pressure happens to jump up much higher, what it's going to do is force its way past this plunger, kind of pushing it down, regulating the gas flow downwards. It's going to exert more pressure on top of the diaphragm, also closing the valve. So regardless of what the incoming pressure is, it's going to be regulated both to the atmospheric pressure and it's going to be regulated to the incoming gas pressure. So now we have a valve that's actually functional. This is a valve that you could use. I wouldn't use this one specifically, but if you brought a well-designed one, it would actually function and be safe to use.
So Dave,
we're getting. Oh yes.
So question for you is that atmospheric that little tube you show going to the atmosphere, is that also the tube that I remember on the TI boiler and on some of our other boilers, we had a little sucky tube that went over to that.
Yes,
that
we
came
did.
from the intake over to it. It's not on the new boilers because we don't have the pipe coming in going over like we used to. Now it's open in the cavity on the TFTN and the TRX and the FTVN.
Yes. So I called it like in the simple gas in a very simple atmospheric boiler that is open to the atmosphere effectively. In a condensing boiler, it's typically open to the incoming air. So even though we no longer have the tube like we did on the TI series boilers, we still have the tube. And what I mean by that is the whole cabinet of the boiler is the feedback tube. So the cabinet will get a negative pressure in it when the fan kicks on, pulling air out of the cabinet, which is going to have the effect of sucking on this tube. So even though there's no tube there anymore, the actual cabinet is the tube. I actually have a couple of slides a little later getting more into what this feedback tube does.
So that's why when we put the cover back on after we've done a combustion analysis and we see the CO2 go up a point or two and this CO go up a little bit, that's because we've now enclosed the cabinet, correct?
Yes, you're changing the pressure on the feedback tube and you're causing the valve to make a change to the air fuel mixture.
God damn it, Dave, you always teach me something. I love you.
So our standard valve assemblies here. So the question is what opens this valve here? And the answer is the combustion blower fan. So this blank square here represents sort of the burner, roughly speaking. This is our fan. This is our air intake pipe from the outside world. And this is the gas line that connects the valve to the bottom of the venturi or to the fan. So what's going to happen in a typical boiler assembly, and I've actually got the order of operations wrong here, so I'll have to correct that for the next video, but in reality what happens is the fan starts first, the solenoid opens second, and then the suction from the fan will actually cause this diaphragm and regulator to open up by drawing air through here. And what that's going to do for us, of course, is drop the pressure above the diaphragm, allowing our diaphragm to rise and allow some gas through with it.
Mhm.
This is fascinating.
So there's our fan starting, and of course it lifts up our diaphragm and The faster the fan spins, the harder it's going to pull. So the faster our fan spins, the lower the pressure in this pipe, which means that we pull up on the diaphragm harder. Provided there's nothing pulling back, the diaphragm is going to open wide. If we slow the fan down to a lower speed, we're going to increase the pressure here, so our valve is going to regulate closed again. So all of that is designed to balance out very well so that we get the right amount of gas, and regardless of the speed that this fan is running, we get the correct amount of gas to burn the correct amount of air. So we're slowly improving to a fairly functional valve. And what we're going to do now is we're going to add the feedback line that Steve was talking about earlier. He's jumping the gun on me.
Oh, sorry, dude.
No, it's all right. So the feedback line is designed to directly tie the diaphragm in the valve back to the air intake. And what that means is the pressure in the air inlet pipe of the boiler is going to directly affect how the valve operates. So again, we're going to start our fan. Our solenoid opens. I got it right on this slide. So as the fan speed is going to increase, we're actually going to lift the diaphragm harder. And that means we're going to get some gas flow through. The other thing that will happen in this scenario is as we speed the fan up, we're also getting a higher negative pressure or suction in the intake pipe, which is actually going to regulate the flow downwards. And the reason we do that is if you have 5 feet of venting, you're going to have a lot less suction pressure here than you would if you have 150 feet of venting. So the difference between those two can be as much as 7-8% of the boiler's output. So if we sent you a boiler that was correctly configured with 5 feet of venting and then you put 150 feet of venting on it and there was no proper feedback to the valve, you could actually overfire the boiler by 7% or 8% just by hooking up the venting. So obviously we don't want that. What this feedback line does is it allows the valve to effectively close off as we add more venting so that we get less gas flow to match the fact that we have less airflow. And we know we have less airflow because there's more suction inside this air intake pipe.
So Dave, would humidity affect this? If it was like here in Philadelphia, we have we can go up to 95% humidity. It's just the atmospheric pressure. It has nothing to do with humidity, correct?
It's just atmospheric pressure, and yeah, so the answer is in as much as the humidity has an effect on the air density, it has some small impact, but because we've got a feedback line, so what has a bigger impact is cold versus hot air. So if it's 95 degrees out, the air is less dense, so per cubic foot of air, let's just say for argument's sake, you've got a half an ounce of air per cubic foot. On a very cold day, you might have 3/4 of an ounce of air per cubic foot. So there's 20% more air. What that means though is it's harder to move a more dense fluid. So it's harder for the blower to suck in cold air, which means you're going to get more negative pressure here. So you're actually going to help reduce the gas flow. So it ends up balancing out.
So this will, no matter what time of the year you do your combustion analysis, it's not going to change. If you do this in the winter when the air is very dense and the pressure is higher, it's going to regulate itself to be correct mixture when we have a hot day and the air's thinner.
It's not bad, but it's not perfect.
Okay.
So you would recognize this as being an old car guy. If you took your car up to Colorado, you'd have to retune your carburetor.
Absolutely.
You'll notice the gas valve has effectively no electronic components. It's got a solenoid that's on or off, so it's open closed. Everything else is done with springs and diaphragms. So while it has the effect of compensating for changes in air pressure, it's not a perfect compensation. The only way to get that kind of perfection is to probably spend $1 million on a gas valve, and each individual valve would be $1 million. Or you have electronic feedback, which is why a lot of cars, of course, have gone to electronic fuel injection. For the purpose of what we do with the boilers, typically what we'll see is a couple of tenths of a percent CO2 change from summer to winter. So it's such a small change that it works so well that we just don't have to worry about it.
Cool.
Question, Dave. The that air vent, which previously was connected to the intake air
Mhm.
because it was basically sealed combustion, is now just open to the cabinet, correct?
It's open to the cabinet, but because the cabinet now represents the air intake, the net result is the exact same.
It is, okay.
Yeah. So if you can imagine, if I was to extend this air intake to cover the entire valve, then this tube, even if it wasn't connected to anything, would be still referencing the air intake pressure. So in a perfect world, what our regulator and feedback line are designed to do is we want to balance the pressure that is coming in this gas line, and we're trying to make that pressure equal to the pressure in the intake. So that's why we call it negative pressure regulated. We're running the intake at a negative pressure.
Mhm.
And in a perfect world, what NTI does is we set our gas valve. So let's just say, for example, you're running at negative 0.25 inches in the air intake pipe. That means the gas pressure in this pipe between the blower and the gas valve will also be negative 0.25 inches. And if
Mhm.
you have it exactly the same, that means you've got a zero offset. If you measure the difference in pressure between here and here, you would show zero difference when the valve is open and working correctly. If you have a negative offset, you would show a negative number here. If you had a positive offset, you would show a positive number, meaning that you're getting more gas than you are air.
So does that make
So
it
of course,
fairly critical? Does that make it fairly
sorry.
critical that the cabinet is actually sealed?
Oddly enough, no, because if the
Okay,
cabinet's not sealed, it effectively means you've got a larger air intake pipe. So it means the boiler has more available air, which means that you get more available gas. So the valve still balances out. Um, yeah, so oddly enough, it probably means that it's less sensitive to problems than it would otherwise be.
So if the door gasket, I had a situation the other day where all the wires were whistling, and I said, well, it's easy. I said, put some thumb gum in those and see what happens. It's just a thumb gum's like a silly putty that they make for ductwork to seal ductwork, and I said, just put that in all of them and see what happens. And he called me back. He called me back a half an hour later. He says, "Yeah, you're pretty smart." I said, "Why is that?" He says, "Well, we used a low profile vent and they extended the intake too far. And it was up against the flat plate. And when I sealed all those holes, the boiler wouldn't fire because of the sealed
Yep.
combustion, which of course they were rewarded. But I guess the question always arises." What happens when those gaskets, 15 years down the road, when those gaskets are breaking down, it's allowing air seepage through them? What's going to happen to combustion?
well, that's
The
good.
combustion will change slightly. If the valve is working properly, it would be sort of the difference that you would see between summer and winter, or the difference you would see by taking the cover off and putting the front cover back on. So when everything's working well, cover off versus cover on is 0.2% CO2. That'd be the same thing if you lost all the seals in the cabinet and they all fell out and rotted away. Effectively, you'd be just drawing room air, and the valve would still work, the boiler would still operate, but you'd be drawing room air as opposed to outdoor air. Which actually, just as a warning to everybody out there, I had this recently. Boiler installed in a pool room. This is a tiny bit off topic, but it's kind of pertinent to the conversation.
Mhm.
Installed in a pool room, clogged up the condensate drain after 3 months. They had previously had an old TI boiler there, and they never had any issues with getting much dirt in it. But obviously, the difference with the new boiler is it's a sealed cabinet versus a direct vent to the outdoors, which means that any holes you put in the cabinet for wiring, if the cover's not fitted correctly, if you don't put the screws back in, you get air leakage from the room. And because all the pool chemicals were stored in the same room as the boiler was rotting out from the inside,
Right.
because effectively it's drawing a bunch of room air now, whereas it previously did not. So my advice to that contractor was to clean the boiler thoroughly, go through, and if you have to, tape off every wire. I didn't know about thumb gum, but I do now. So put some, duct sealant on anything that could leak, and just make sure that all the air for that boiler comes from the outside world, because pool chemicals and condensing boilers are death.
Absolutely.
All right, so back on topic. Oh, again, our valve opens. And in a perfect world, what you're doing when you're setting the offset gas pressure, so you're going to make your adjustment to this regulator, you're tightening or releasing tension on this spring, you're allowing that spring to fine tune the gas pressure. Oh, excuse me. And when we're correctly set, the gas in the gas pipe will be slightly negative compared to the gas in the air intake pipe. And that means we've got a negative offset. So if you were to take your dual port manometer and hook one port here and one port here, you would see a difference of maybe negative 0.1 inches or something to that effect. The valve isn't really set up to allow you to do that, but that's effectively what we're doing when we're setting the offset pressure. The reason we want a negative offset is we want the boiler to operate safely under a wide range of conditions. And the way we do that is we prevent it overfiring anywhere. So it's safer to have the boiler run lean than it is to have it run rich. And the negative offset means that as we reduce airflow, the gas flow reduces just a little bit faster. So now we get to look inside a real valve. It's a real boy. So this is a valve off of a TX product. For those of you that have been with us for a while, you will have seen some of these valves, hopefully not disassembled quite like this one is. So here's our parts again. There's the big rubber diaphragm we talked about. This little brass hole or ferrule here is actually connected up to the regulator. And so that feedback line that I talked about before actually passes through this brass. And I'll say it pulls on the bottom of this diaphragm. And our gas line connection's over here. And then of course the solenoid at the top. Now, when we start to disassemble this valve, what you see inside here is there's the regulator plunger that we talked about at the bottom. The little spring is kind of hidden inside this cone. And of course, there's the diaphragm sitting on top of this assembly. And what I'm simulating here is I'm pushing down on the diaphragm with my finger, and you can see that the regulator is fully open. And on this side, the regulator is fully closed. And hopefully, I'm going to show you on the next slide, hopefully where the gas passes through this. It's a little hard to draw because I don't have three-dimensional drawings available. But your gas enters through the vent screen here and it goes up into the top. It's prevented from entering this central chamber by a diaphragm that's controlled by the solenoid. This little plunger here is controlled by the vacuum, and you can see these two holes up in the top here. And you'll notice those holes correlate to this cavity here, which is directly connected to the outlet where the blower would go. So as our blower draws more air, it's going to pull a vacuum, pulling this diaphragm in the downward position. And if we go back one slide or two slides, and this little ferrule is tied, in this case on a TX, directly to the air intake pipe, which is actually pulling up on the diaphragm. So I've got the blower pulling down on the diaphragm, the air intake pipe pulling up on the diaphragm, and those two are fighting each other all the time. So what ends up happening is gas moves into this central chamber once the solenoid opens. It passes around the diaphragm into this cone here, and it'll exit through these two ports up at the top. So it exits from them, goes into this cavity here, and then it can get out to the blower assembly and hopefully get burned in the combustion chamber. So let's have a quick look inside the valve. So this is the same valve. This is the central chamber I was showing you earlier. This is your solenoid here. So the solenoid is pulled open by this. Gas is going to pass in through a little screen, enters the central chamber, gets from the central chamber into here. And this guy here is the gate valve. This is the adjustment screw for high fire. So this is a coarse adjustment that allows you to set the maximum possible gas flow. So our gas comes in, it can't get through until the solenoid opens. Then the solenoid will open, so gas is now going to pass into the central chamber. Vacuum from the blower is going to open the internal diaphragm and hopefully allow gas to pass to the outside world. And I just included over here another shot of the gate valve. So the adjustment screw for this is sort of up in this area here. You can't quite see it, but it's adjusting this gate valve. So if you fully close that screw, you'll actually close this hole off completely so no gas gets out. This is the feedback tube line, this little brass tube up here. This is your low fire adjustment. And that's again where you're controlling how much that internal diaphragm opens and closes.
Mm-hmm.
And just a quick reminder on the TRX, FTVN, and the smaller TFTN boilers, this is the kind of valve we're using. You've obviously got your offset screw here, which is the low fire screw. This is the diaphragm, or the internal diaphragm adjustment, if you like, or regulator adjustment. You've got a throttle screw, which again is just a gate valve that sets the gross gas flow. And then of course you got a line pressure test port right in the center here, so you can make sure you have adequate incoming gas pressure. So next up, we get to talk about the Venturi, and it's, I think, a fairly misunderstood component. It's a very, very simple device. It doesn't have a lot of moving parts, but it provides a very, very important job for the boiler. And so because of the way we have our regulator set up, getting the correct pressure at the suction, if you like, on the gas line is critical to getting the right amount of gas into the boiler, because what's happening here is we're sucking gas through this line here. We're going to mix it with incoming air, and we need that to burn correctly. So in order to get the right amount of gas, we need the right amount of suction. So that's where we get into the Bernoulli effect. So thankfully, there's no math. So for anybody that's panicking and jumping out the windows now, I'm not going to make you do any math. We're not going to do any fluid dynamics. I couldn't do it even if I wanted to. So we're going to do a little bit of science here, and hopefully it's fun. So the Bernoulli effect, that's this guy here, Daniel Bernoulli. He was around in about 1782, or at least that's when he passed away. And he was the guy that coined this term. So he was the first guy who mathematically discovered how to measure this and how to put numbers to it. So that's what he's most famous for. He did do a few other things in his life, one of which was he contributed to the invention of calculus. So I don't know, I guess some men just want to watch the world burn. But anyhow, so what I want everyone to do is hold a piece of paper up to your mouth like this. So watch Steve if you can see him, and just blow firmly across the top of the page. And before you do, I want everyone to answer the demo question, or the question. What's going to happen? Is our paper going to go down? Is it going to go up? Is the paper not going to do anything? Or are you wondering why the heck we're talking about paper in the first place? So poll's open. Don't cheat. As soon as you answer the poll, you can do the demo.
Two-thirds are thinking it's going to move up.
12% say it's going to go down. 20% say it won't change, Ted.
That's right.
Wow. You got another 40 seconds to answer this.
We're all over the board on this one.
Wow.
Although I have to say the ones that are saying, why are we talking about paper, are just being a little bit sarcastic.
Well, let's hope, right?
And you got 15, 12, 8, 7, 6, 5, 4, 3, 2. All right, give the final there, Ted.
Well, I have to say we have a lot less consensus on this answer. 57% say it's going to move up. 17% say it will go down.
So Ted, you're the guy we volunteered, so I'm gonna give the screen back to you.
Okay.
I think.
Right.
And then you get to be the demo guy for
I get
anybody
to
that
be the
doesn't have
demo
paper.
guy. All right. So I'm holding
Change
the
presenter.
paper.
So I'm gonna go with Mr. Wieland. Okay, can everybody see Mr. Wieland? Is he up in full view for everyone? Either that or Ted.
He's ready to blow.
All right.
Okay.
So what's happening there? Steve is blowing against the paper, but somehow the paper's moving up towards Steve. What's going on?
It looks like 57% had it right.
And 57% did have it right. So there's a common misconception when we talk about flow and pressure, and I understand where it comes from, and I was guilty of it until, well, not that long ago, to be honest. most people, when you think of increasing flow, for example, they think of standing in like a river, and they're thinking of the water pushing against them and knocking them off their feet. And they think, well, the faster the flow is, the higher the pressure on me. But that actually isn't pressure in the sense that we're talking. That's a different property called flow head, which is effectively the mass of the water is kind of knocking you over. But the pressure the water exerts on you is pressuring all sides equally at all times. So we're going to go back to the presentation. So Steve,
Pretty
okay,
gave it
yeah,
to you. You got it.
perfect.
By the way, Bill Mackey says that's the same way that the airplane wing
Yeah.
used.
I was just
That's
going
how
to
I
say
first
that
learned about
myself.
this.
Yeah.
I was a bit of an airplane geek as a kid, and I had to do a science project, and that's the first time I heard about this fellow from my parents' Encyclopedia Britannica.
Tell us
So
the truth, Dave. We know you still are.
yeah, I'm still an airplane geek. Yes, I absolutely am. I don't know if you can see up on the wall behind me. There's a couple. There's a Thomas More Scout up there and an F6 Hellcat. So
I love it.
our paper is going to move up, and get my cursor in the right spot here. And now we've got another demo for those that are interested just to try it. So Steve, I'll put you back on for a sec. Can you fold your piece of paper into a tent like shown?
Just
So nice, neat
fold it
fold
in
in the
half
middle.
lengthwise, like this.
Yep, nice, neat tent basically.
Okay. By the way, you're showing you just nixed your PowerPoint, and
Now
we're
we're
now
showing
looking at your
your computer.
files.
Are you
Yeah.
now watching me?
I
No,
know.
well, we can see you, but we see all your files. We don't see your presentation.
Oh, okay,
I
sorry.
went back to now I'm the presenter. I got it.
Okay, while you do the presentation, I'm going to fix my screen.
Okay, so
Right.
I'm supposed to do this, right? And I'm supposed to
Put
have
it
this
on a hard,
top of
flat
something like
surface.
this,
Yep.
and I'm supposed to blow
And
down on it.
now there's another poll question here.
Okay. Well, ask the poll
So the
question
poll
first.
question is, yep.
Okay. So I'll launch that, and of
Right.
course the wow, what happened to all of our screens?
So
Blowing through.
let's say while you get yourself organized there, the paper will blow off the desk, choice A. Paper will flatten, choice B. Paper will not change, is C. And paper will fold back up, D.
Yeah. So what you're going to do is you're going to blow right down the middle of the tent, and what's going to happen to your paper?
Feel free to start answering.
I think everybody's too busy trying to fold their paper in half. I think. I mean,
Hey,
for goodness sake,
yeah,
folks.
you're supposed to answer the question and then fold the paper.
Right.
I
That's the
need to get these things in a different order somehow.
Yep.
So how are we doing for time on this? Oh,
So
we're just about out of time. All right, 1 minute, here we go. 14% chose A, paper will blow off the desk. 33% choice B, paper will flatten. 14%, paper will not change. And there's a tie between B and D. The last choice at 36% also was paper will fold back up.
yeah, so 36% say it will flatten and 36% say it will fold back up. Wow.
Right.
So I'm going to close that poll and maybe we can get our cameras back. There we go. Cameras are back. And so now I'm supposed to take a flat surface and put this on here, right, Dave?
Yeah. Can you see me as well?
Blow down on it, you said? Blow down on
You're
it?
going to blow right through the middle.
So I'm going to blow right through the middle. Oh, that's really weird. It closes in on itself.
Yeah. Here, watch,
I'll
guys.
do that again. Wait a minute.
Can you see me?
Yep.
Yeah.
Nope. It works way better when it's on your desk.
Yeah, it
It
does.
worked pretty well for Steve. It folded right up.
It actually does work pretty well. So normally there's, well, one of two things typically happens. I guess what's happening to Steve's is not what I was expecting, but see how it flattens down when he blows through it?
Yep.
That's sort of what you normally see when it's sitting on a flat desk and you get a nice straight shot. And what's happening there is, and let's put the presentation back on because we get to talk about our friend Daniel.
Wait a minute. I got to get back to you. Hold on a second. I have to somehow get you back onto being the presenter.
Oh, here, I can do it.
Okay,
There.
wait. Now you're the presenter again. You should be able to do it now,
We're having an
Okay.
Andrew Smith moment.
I think.
Oh, we are. Okay, there we go. Are you back on
Yep.
the gas?
Yes,
You're
yes.
showing the wrong
But
screen. You're showing your
you're
actual
not in
PowerPoint.
presenter mode though.
Go back to the presentation. Wrong screen.
There we go.
Yep,
There
there
we
you
go.
go.
Better? Okay. So
Hey, we're
normally
doing
what
pretty
happens
good for
is,
switching organizers back and forth so many times. This is good.
Right?
yeah.
I'm glad I got the easy
So,
job. I just have to read the poll.
okay, so we know what happens now. Oops, wrong way. So what the Bernoulli effect is describing is that and in fancy language, as the dynamic pressure of a fluid increases, the static pressure decreases. So what that's a fancy way of saying is that as we increase the speed of the flow of any fluid, whether it's air, water, gas, doesn't matter, through a restriction, the pressure is actually going to drop at the fastest point. And then when the liquid or vapor slows back down, the pressure is actually going to go back up again. I figured it was a lot to ask everybody to go and build one of these and put manometers on it. So you're just going to have to take my word for it. If you made one of these, and Steve, I was saying earlier that you would know about this because you're an old whatchamacallit, car guy.
Oh yeah.
You'll notice the shape of this looks an awful lot like what you'd find in the barrel of your carburetor.
Yep.
And typically here at the point of least pressure is where your fuel gets entered. It gets sucked in.
Right.
Mhm.
Oops, wrong way. There we go. So Bernoulli's principle, again, key concept in fluid dynamics as it relates to pressure, speed, height. It states that an increase in the speed of a fluid occurs simultaneously with a decrease in the static pressure energy or the fluid's potential energy. And I did some tooling around online from physics people to try and understand exactly what's happening here. And the best way to think of it as you push the liquid through that narrow space, it speeds up. But in order to speed up, it has to gain energy. But since we know that you can't create or destroy energy, the energy has to come from somewhere, and where it comes from is potential energy. So when you have fluid sitting in a pipe doing nothing, it's exerting a pressure on the outside of the pipe. So typically for our boiler systems, it's 15 psi, for example. Well, if you take some of that 15 psi of potential energy, and we call it potential because until you get a leak in the pipe, the water doesn't do anything. It's just pressing and not moving. So if we take some of that potential and turn it into a type of kinetic energy, we can increase the speed of the water. And that's where the energy goes. So this Bernoulli fellow figured out that in order to maintain I think it's the first law of thermodynamics, that you've got to conserve energy. The energy has to come from somewhere, and where it comes from is the change in pressure. And at some point, I'm hoping to actually build a live one of these that we can stick in our lab in the St. John training room. But basically what you can see here is we've got low velocity water coming through. It goes through restrictions. So in order to get the same volume of water that was here through this little pipe, it has to go faster. When it gets into the bigger pipe, it gets lazy and slower. And that means that it exerts more pressure on its container. So now we're going to go through what a venturi is, and a venturi takes effect of this Bernoulli effect by creating a narrowing of the air intake pipe. So this is a cutaway of the venturi that's used on our TRX FTVN boilers. Don't know what happened there.
I don't know.
There we
There
go.
we go.
There we go. You're
Okay.
back.
So we've got our gas orifices here. So as we create a low pressure where my cursor is, we're going to suck on these gas orifices to pull gas into this chamber area here. There's a couple of flappers. They're right here outlined in yellow. And there's a light one and a heavy one. So the purpose of the light one is it actually blocks this orifice at low airflow rates. And at lower airflow rates, the heavy flapper actually keeps the bottom half of the venturi closed, which means that the air moving through this part of the venturi is going to move faster, exerting a higher suction, if you like, or a lower pressure on this orifice, meaning that this is then supplying most of the gas flow when the boiler is running at low fire. When we start drawing more and more air, what's going to happen is this flapper is going to lift up, as is this one. We're now going to double the amount of airflow, but we're also doubling the number of holes that let gas in, and this gives us a much better turn down ratio on the boiler. This lets us get 10-to-1 instead of 6-to-1 like we had on the old TI series, for example. So we've got an aluminum housing that just lets you bolt things on, connect your gas line, and it holds the whole assembly together. And of course, the plastic insert, which is all the black part here, that comes separate from the aluminum housing, that's just the way we sell them. Okay, so we've got our rough rendition of an air intake pipe. Of course, the air has to squeeze down and get small in order to go through those openings. As it does so, it drops the pressure inside the venturi. Hopefully at this point our valve is opened, allowing the gas to mix with the incoming airflow. This all gets chewed up in the blower and mixed together very evenly, and hopefully we get a nice clean air-fuel mixture. So if you go through this, so it says I'm not an engineer, why do I care? Well, I guess the answer hopefully is that if you know better how the valve works, you'll better relate to the ways it could fail and how these things can affect you in your daily troubleshooting life. So if we got our gas valve again with our blower running, we're going to let gas into the valve. The valve's going to get opened by the suction of the airflow. We're getting gas through. So far, everybody's happy. And then one of these guys comes in and moves into the air intake pipe. So I don't have a poll question for this, but I'll just ask everyone to think about this for a second. If I stick a mouse or a mouse nest, whatever it is, in the air intake pipe, I've seen golf balls, matchbox cars, water, rocks. I'm trying to think what else I've seen that's interesting. Wasps' nests, bees' nests.
Tennis
Ted, do you
ball.
have anything to add to that?
I found
Which
a
was the one,
tennis
Ted?
ball. I found a tennis ball.
Tennis ball. We had a snake in one the other day.
Yeah.
So as I restrict the airflow coming in and try and suck it past the mouse, what's going to happen to the suction pressure in this section of the venting? And the answer is, if you've ever tried to, has anybody ever gone out and got one of those thick strawberry milkshakes at like McDonald's or whatever, and you're having a nice drink on the milkshake, you're sucking on the straw, and all of a sudden the strawberry sticks in the end of the straw, and you basically try and suck yourself inside the straw? Well, the same thing happens to the air intake. The pressure here is going to drop dramatically. That's going to have the effect of pulling down on this diaphragm, which is going to choke off your gas flow dramatically. And if the blockage is big enough and the valve is set correctly, what we're actually going to do is just shut the gas off entirely. And you might not get an air, you might not get a fan error, you might not get any other air, but what will happen is your boiler just fails to ignite or can no longer stay lit because there's not enough gas to support combustion. Another scenario that happens, of course, and this one's a little less common, but we still see it, is our mouse friend, rather than getting into the air intake, decides that he would like to go move into the exhaust. And of course, that tends to be a one-way trip because once the boiler does kick on, he's not going to last very long. So now what's going to happen is we're not going to get a lot of suction in the air intake pipe, but we are going to get less suction on the gas side.
Scotch goes this way.
So by preventing air from exiting the blower, if air can't exit, that means air can't enter. So the pressure here is relatively high, so that doesn't have a big impact on us. But if we can't get air to exit, that means the pressure in here is relatively high, which has the same effect. It forces the valve to go closed. And again, our boiler either runs lean all the time or shuts off due to a lack of gas flow. And the biggest reason I bring this up is not so much that it shuts it off completely. I think most of us sort of intuitively understand that if you have no air, you're going to have no combustion. But the effect that a restriction has on combustion is quite profound. So if you have this exhaust vent or intake vent blocked 50%, the boiler might actually run just fine, but you may have real trouble setting your combustion. It'll be too lean. Sometimes it'll be too rich. You may have a lot of error codes where at a certain fan speed, typically very low or very high, where the combustion numbers just go funny and don't stay doing what they're supposed to. And that all has to do with limitations of what the gas valve is capable of compensating for and how severe these restrictions are and how well set the valve is. So if we don't have this regulator set properly, it can actually allow too much gas flow even though there is a mouse in the exhaust, or we could have it set the other way where it's too restrictive and it won't allow any gas flow with the tiniest restriction. So you've added 10 feet of venting and all of a sudden the boiler stops working. So that's how this all interacts together. Obviously the valve, the venturi, and the blower, we typically buy them as a system from a manufacturer that spends a lot of time making sure all this works together properly. And then we take this and install it into a boiler and test it and make sure that it works with our burners and the other stuff that we want to do with it.
So Dave, a question's come up. Can you use and I love to say this, can you use a manometer or a manometer to measure the intake air pressure? And if so, what should the pressure range look like?
Yeah, that's a very good question. We actually have taken in tech support, and I don't know why. I only started doing this about 3 years ago, so it took me 15 years to figure it out. Run the boiler at full fire. If you have, and this is for residential size boilers, so I'm going to say that's basically the 200 and down. If you're running 3-inch venting, you're going to have a negative pressure somewhere in the region of 1/4 of an inch, so 0.25 inches water column of suction pressure in the intake pipe. And the way you would test that is if it's a TRX, you're going to do this about 4 inches above the top of the boiler. You're going to drill a very small hole in the pipe. You're going to shove your manometer tubing, about 2-3 inches of tubing inside the pipe, run the boiler at maximum fire. And if you have negative 0.25 inches on 3-inch venting, you're fine. Anything up to a negative 1/2 inch would be, perfectly normal, even if you're running 150 feet of venting. On the exhaust side, you can use the exhaust test port on the boiler and do the exact same thing. Take 2 or 3 inches of manometer tubing, shove it into the exhaust test port, run the boiler at its maximum firing rate. And again, typical back pressure on 3-inch venting is going to be maybe up to 1/2 inch. It's very low.
Could you do that by just disconnecting the low voltage wiring going to the blower so it runs at full speed?
You can, but the pressure readings are going to be higher than what I indicated, because at that point you're actually over revving the fan. You're running it at maybe 125% of its capacity. So because you're trying to move more air, you're going to create a bigger pressure difference. But certainly you could. Now, there are some downfalls to that test. So one downfall, for example, would be if the mouse happened to be living, right here, right next to the blower, or if he's living anywhere before the point where you take your test. So if you're testing outside the boiler cabinet somewhere down bottom right-hand corner here, and the mouse happens to be up where this air intake sign is, you're not actually going to get an accurate reading because the mouse is up here affecting your airflow. So if the venting is clear and clean, what I can pretty much guarantee is you'll get a very low pressure. If it's 2-inch venting, the pressures typically range up to about 1.25 to maybe 1.5 inches on the extreme. So 1.5, I'm going to say, is the maximum you should see on 2-inch venting ever. If you're on 3-inch venting, typically never more than 1/2 inch, and that's suction or positive pressure, depending whether you're checking the intake or exhaust. But again, if you have a blocked burner, so if the mouse is inside the burner, which we have had happen a few times, you're not going to get the right suction pressure or the right exhaust pressure. So it's always important that before you take those readings, the burner itself has to be clean, the combustion chamber must be clean, and you want to make sure that there's no obvious obstructions that that you can't see, sort of thing. But it is a good way to detect a blocked intake or exhaust without doing, without getting the bore scope out or cutting venting. Okay, and this is the last slide, guys. So this is just a picture of a damaged venturi. It's the best photo I could find, but if you look inside here, you'll see the inner lip of the venturi where my cursor is, and you'll see it's all chipped and broken away. And the complaint here is that you could no longer set combustion on this boiler. And the reason you could no longer set combustion, because this lip was missing, we've effectively increased the size of the venturi. And we know from Bernoulli there that if we make this hole bigger, that means that the pressure that the pressure drop it creates is going to be less. If we get less pressure drop, we get less gas flow. And so even the tiniest bit of damage on this Venturi has a tremendous impact on the amount of gas that gets into the boiler. And so of course this boiler just could no longer be set. I think it was on propane and we could get 8% CO2. That was the best we could hope for. Put a new Venturi on it, and of course it worked great. So, all right, guys, that's the presentation for today.
Thanks for watching the video today. If you'd like to check out more videos, see the link below. Don't forget to like, share, and subscribe to our channel for all the future updates. And also check us out on Facebook, LinkedIn, and Instagram.